Okay, welcome back everyone. So in this video, I want to say a little bit more about drawing electric fields, and then I want to take a closer look at the geometry and point out something that I think is very important for us to see. So in the last video, we talked about what an electric field was and how to determine what an electric field looked like. And you will probably have numerous opportunities to draw electric fields of your own, and the process is basically you just have a collection of charges. So let's say I had a plus charge here and a negative charge, and you simply think about, at lots of places, what would be the direction of the force on a positive particle. Now right here, for example, which is kind of in between, our positive charge would push us away and our negative charge would pull us in, and the result of adding those two together would be a force that goes, I think I'll do a different color for that, a force that goes kind of sort of like that. Okay, now we could do this at a lot of different places. We could do this right here, and we'd have a very strong pushing away force and a weaker pulling force. So I'd get something going like that. Oops, forgot my color again. And let's do this in one more place. Let's do it right here. I'd have a really strong attraction force there, and I'd have a relatively weak repelling force from the positive. And if I put those together, then I get something like this. Okay, now I'm going to see something similar if I draw things on a line directly between them, and something kind of symmetric over here. Whoops. And so what I'm getting at is that what we can do is we can draw the electric field by connecting forces. What do I mean by connecting? Well, I mean we kind of make a smooth curve that kind of flows through space, kind of sort of like this. And that is what we call field lines. Okay, so we can draw other field lines. There would be field lines going away from this positive, okay, and there would be other field lines coming into this negative, and we have a couple of basic rules about field lines. So rules about field lines. Number one is called the Ghostbusters Rule. In Ghostbusters, the most important thing was don't cross the streams. And with the field lines can't cross. And the reason behind this is that it would cause a contradiction. Because what is a field supposed to be telling us? It's supposed to be telling us the direction of the total or the net force on a charged particle. So if, for example, here's my point and I had one field line going like this and another field line going like that, well, what that would tell me is that there's a net force going this way and there's a net force going this way. And that's not possible because there's only one true net force. Okay? So, will the real net force please stand up? Please stand up. Alright, I can't believe I just did that. So anyways, there's only one net force. That's rule number one. Rule number two about drawing field lines is that the number of field lines is roughly proportional to the amount of charge. Let me give you an example. And this is a way for us to keep track of things, because otherwise we could just draw tons and tons and an infinite amount of field lines and it wouldn't really mean anything. So if I had, for example, something with a charge of plus 2q, and over here I had something of minus q. Okay, so the way that I would start this off is I would just pick a random number and I would say every q has 8 lines. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Alright, well that means that if I have 2q over here, I need double that. So I'm going to put in my original 8. They're supposed to all be the same length. And then I would put in 8 more for a total of 16. Okay, why is this important? Well, because what's going to happen is that we're going to have some connecting of these field lines between a positive and negative, just like we did up here. Otherwise, they're going to cross and we're going to have issues. Okay, so this won't be a perfect drawing, but this one connects like that, and then the next one connects like that. Well, it's supposed to be a little bit smoother than that, like that. The next one connects like that, and really that's not there anymore. Okay, and the next one goes out like this and comes in kind of like that. It goes in and comes out along that one. Okay, and that's pretty much it. And then the rest of these just kind of go off into space. Okay, and these come in from wherever. But the important thing is how to draw them in between here. Okay, and so that's a very important rule. It allows us to kind of see how to draw the relative strength of an electric field. Okay, last point. Now this is a little bit more serious, okay? There's a different way to write the constant k, which is basically 9 times 10 to the 9th. The other way to write it is that k is equal to 1 over 4 pi times a weird constant epsilon naught. Okay? And this is a constant which describes how easy it is for electric fields to move through space. And in this case, when we talk about epsilon naught, we're talking about a vacuum. There's other epsilons that don't have the little subscript, and those are for different materials. So electric fields can go through air, they can go through water, they can go through anything. Well, most things, okay? And this constant epsilon tells us how well electric fields do this. But this is very important because now if I write Coulomb's law without the k, it looks like this. Q1, Q2 over 4 pi r squared epsilon naught. Okay, now why did I write it like that when I should have put the r squared at the end? Well, because now I can rewrite it like this. And this looks even stranger, right? 1 over 4 pi r squared times q1 q2 over epsilon naught. Okay, now this is where we need to stop and take a look at a 3D model of an electric field. And we're back. This is a 3D model of a positive charge electric field. You could see on the screen here that there's a bunch of different units. This is from an online course called RICE 102X, and it's part of the edX website, and you can find lots of different simulations, but this is part of a course which is aimed at students taking physics at the undergraduate level, or basically what you will see in 3-4 Chem Phys. Okay, but what you can see here is what an electric field looks like. That it's really a 3-dimensional object. These arrows are pointing out radially. Okay? Now what's the importance of this? Well, I want to think about how much this electric field is spreading out. And so imagine that I take a balloon or some sort of thin membrane and I put it around this charge. And I want to know how many of these arrows are going to go through that surface, okay? Well, let's do it kind of like this, okay? Here's my charge, and surrounding it is a sphere, okay? So this is a sphere of radius r. Okay, so what is the electric field doing? Well, we just saw it's going out in every which way. I can't make it 3D, but you get the idea, okay? Now, what happens if I try to figure out the surface area of the sphere? Well, think back to geometry. The surface area, I'll do it over here, A is, are you ready? 4 pi r squared. That's the surface area of a sphere. And so now, this gives us some important insight into all inverse square laws. The real question is, why? Why are inverse square laws 1 over r squared? And the reason is this. We live in a three-dimensional universe, and when we think about forces like gravity and like the electric force that seem to spread out through space, if we put a surface around and look at it, basically what we're saying is that the force is proportional to some stuff divided by the amount of space that force has to expand into. Okay? And there's a very famous law in physics called Gauss's law that you'll study later on involving the electric field. And I just wanted you to start thinking about it now, that isn't it kind of strange and beautiful that this area, this 4 pi r squared, shows up in the electric force equation. And it also shows up in electric field. Electric field is Q over epsilon naught times 1 over 4 pi r squared. Remember that electric field was KQ over r squared. Same thing. And believe it or not, it shows up in the gravitational field. Remember, the gravitational field was Gm over r squared. And likewise, you can write this as 1 over 4 pi r squared times big M over some other constant, which involves big G. Okay? The crazy thing about both the electric and gravitational fields is that they're spreading out through space in a spherically symmetric way. And this is really all I want to say about this for right now, but I hope that you at least see this and appreciate the geometry of what's happening here. Okay, so that's it for now, and in the next couple of videos you'll see some examples of how to work problems with the electric field.